So let's talk about splitting your data set, why it's important, and what are the typical splits that you can have. So you remember that we have this long pipeline of data preparation, and that pipeline ends at scaling, but we have this important splitting point here in the middle. And really, if we wanted to represent that pipeline a little bit more realistically, we would do something like this, where we have, after the splitting, a training set, which is the set that we will use for training our model, and a testing set, where, as its name suggests, we'll use this data to test our model. But why does it matter? Why is it so important to split this data set? Let's try to look at an example of data to convince you that not using part of your data for your training is absolutely vital to being confident in the prediction of your model. So let's imagine that we have this set of data here in blue. It doesn't matter what the scale of the axis is because this is just a theoretical example. It's valid for any data that you would have. Now let's imagine that we have a fantastic algorithm that we train on this data, and in fact we train it so well that the algorithm, the trained machine learning algorithm after training looks like this. The red line represents the predictions, and you can see that every data is connected by a red line. Now this has a name. It's called overfitting. When your model is so fitted to the data that there's basically no room for error. And that's a problem. It's a problem because really the difference between the label value, so the blue data point, the true value of each sample, and the prediction, which means where those values would fall on the red line, well, that difference is 0. It's a perfect fit. But now, if you were to take a new sample, something that you want to predict that is not part of your initial data set, let's say that the green triangle represents the position of the true sample. If you use your model to predict the value of y based on the x value of this sample, you will obtain something like this. You have to project it on the red line. So the red triangle represents your prediction for the true value of y of this sample. Of course, it is incorrect, but the point is it's incorrect and you don't know it. And so there's a difference between these two triangles. And this difference, well, because you think that your model is perfect, you think it's 0. So your error bar is going to be very small in your mind, when in reality you have a much larger error. And this is because your model is overfitted, but because you don't have any test data, you basically cannot see this. So let's look at a counterexample where we set aside about 20% of our training data to test the model. So now we have the blue point, which are the training data, and the yellow-orange points, the big round points, are those training data that I've set aside. So the model is still overfitted, but the orange points are not part of the model. So now we can basically use those points to test the model. We see that the error on the training set is equal to 0 because, again, we don't have any difference between our true value that we know to be true and the red line. But when we test our other data set, the orange point, which is our test set, since we know the true value of these set, we see that we have an error on this test set that is much greater than the error on the training set. So thanks to this, we now know that we have an overfitted model because our training set is so much better at predicting the result than our test set. So that means that on the test set, the model is underperforming. And that is a classic sign of overfitting a model. So knowing this, we can revise our assumption and maybe do a simpler model, one that doesn't overfit the data so much. And of course, a good model for this type of data is a simple, straight, linear model, which is represented by this red line. So now that we have a simpler model, we can look at it from the perspective of our training and test dataset. Now, our training dataset and our test datasets have similar orders of magnitude in terms of error. They both have an error, and in fact, we can draw an error envelope for this dataset. So now we have a much better sense of what the true error on our model is. And this is important. Why? Because now think about this. If we take our green triangle, this new data that we want to predict again, it plots here on the edge, and our prediction, of course, is right where the red line is. So the red triangle represents our prediction. So we are off from the true value of the model. However, machine learning model and statistical models are never completely precise. And we know, thanks to the blue area, what our error is. And now you can see clearly that if we report the predicted value with the error bar, then we actually represent the true value of the green triangle, because it's right at the edge of our precision. And that is something we could not have done if we had not set aside an important part of our data set to be able to test our model. So you sacrifice some of the training model as a test set, and it's very important that you never show during the training this data to your algorithm. Because if the algorithm is trained even partially on that data set, you have a risk of fitting to that data and obtain an overfitted model and not be able to see this or to predict this. So the question should be in your mind now, how much data do you put aside? Well, it depends. Classically, if you have a small to medium-sized data set, a split that is commonly used is 80% goes to the training set and 20% of your data goes to your test set. And that's exactly what I showed you in this simple example of the linear regression. But if you have a truly large data set with millions of observations, then you can argue that you don't necessarily need to have as much data in terms of proportion of data reserved for your test set. So maybe you can go down to 10 or even 5% of your data set. And that is really a decision that you need to make based on your data and what you know about it. So there's no fast and hard rules, but what is absolutely vital is to have a test set so you can actually test your model and know if you overfit, underfit, or otherwise if you have any other problems.